continuity in every single class afterwards, so you should know it. So the most basic notion of continuous function is, if you can draw it in one shot, you don't have to lift the pencil. But then there are also functions that are continuous, but you have to draw them from segments, and then they're studied in advanced calc, so you have to lift the pencil. So that's not a best way to describe it. For all of the stuff that you're going to deal with in Calc 1, 2, 3, and so on, continuous functions can be drawn in a single shot. So sine and cosine, continuous. Tangent, not continuous, right? Because you have to draw one segment, then vertical asymptote, then another vertical asymptote, and so on. Functions can be continuous globally, which means they're continuous on the course of their entire existence. And then also functions can be continuous on pieces, right? Piecewise continuous. So we're going to define all of that stuff and then take a look at certain points. So first of all, I'm just going to draw, let's say, e to the x, and I'm going to draw 1 over x, and state clearly that e to the x is globally continuous, right? It was one strike to draw the whole thing, and 1 over x was 2 strikes, so it's discontinuous. And we see that it's discontinuous at 0, x equals 0. So this one is continuous, and this one is discontinuous at x equals 0. So this idea of continuity at the point is the major idea, and we start by defining that first. So definition: function f of x is continuous at the point x equals a if, number one, f of a exists. Number two, limit of f of x as x goes to a exists. And the major one, 3, limit x goes to a of f of x is actually f of a. So on your first exam, I already told you that the definition of a function from the first class will be there. This is one of the questions, along with the Theorem 2, along with those definitions for limits, that for asymptotes, that could show up on the test as me asking, state the definition, state the theorem, or something like that. So if I say, state the rules for continuity at the point, you will write 1, 2, 3, because those 3 are the rules that you need to check for continuity. So let's see how does this work. So we take, say, f of x is equal to 2x plus 3, and I want to see if this is continuous at x equals, let's say, 9. So I want to check continuity. What do I have to do? I have to check the 3 rules. So number 1, does f of 9 exist? Yeah, 2 times 9 plus 3 is? Very good. So it exists. It exists. Awesome. Then we go number 2. Does the limit of 2x plus 3 as x goes to 9 exist? Yeah, right? It exists. Awesome. And then we go number 3. Are they the same? Yeah. Yes, in this case they're the same. So because it passed all 3 of these conditions, we say yes, 2x plus 3 is continuous at x equals 9. Now, we have no clue what's happening at 5, what's happening at negative 100. We have to redo the whole thing for those values. But we know that this function is continuous at 9. All right. Let's check, say, f of x is equal to x plus 1 for all values x larger than 1, larger than 0, sorry, and negative x squared plus 1 for all values smaller or equal than 0. So this is called a piecewise function. It has two pieces, a linear piece and a quadratic piece, and they may or may not connect at the same point, right? One could be above, the other one below. They're definitely not going to be stacked on top of each other because you can't do that in a function. You see that the domain of one is to the left of 0 and the domain of the other is to the right of 0. So they're definitely not stacked on top of each other. But what you have is that you can check continuity at 0. So if I'm checking for continuity at x equals 0, I'm technically asking if these two are connected, right? Because if they look like this, they're not connected. If they look like this, they are. So it's one or the other. Or maybe, like this, whatever. So we can have either of those. So if it's continuous, they will be nicely connected, and you will have one function, and then it immediately becomes the other. So, question is, does f of 0 exist? So, can we compute f of 0? Yes, we can. And where is f of 0? 1. F of 0 is 1. Good. We will be computing f of 0 on this line because that has x equals 0. So we will calculate this as negative 0 squared plus 1, which gives us 1, exists. I usually put just a check mark. I don't spell out this every time. 2, does the limit x goes to 0 exist? The answer is yes, but how do you compute this? That's the one. You have to take it from the left and from the right because this is a piecewise function that is broken at this value. You have to use Theorem 2.2. I'll explain why later because we're going to run into a problem where it breaks. So in order for us to answer this, we have to take a look at the limit x approaches 0 from the left, and the left function is which one? Where is the 0 with the left numbers? Which one? Top or bottom? Bottom. Negative x squared plus 1. And we do get 1, right? And then limit x approaches 0 plus is the top one, right? Because it's approaching from the right. These are values, these numbers are to the right of 0. So we get 1. So because of these two, we have that the limit of the entire function is 1 because they match. If they don't match, then no limit, which breaks continuity. Exists. And finally, number 3, 1 equals 1. checks. So f of x is continuous at x equals 0. It was a piecewise function. And we got it. We checked all three conditions. They all passed. Perfect.
So would this be the function where the two dots are like on top of each other? Like if we were to
But
graph it.
one has to be open, one has to be closed.
Right.
And yeah, they're at the same point.
Right.
Yeah, at the same point. Very good. All right, let's take a look at. I want step function. How about taxes? That's coming up. So I'm not going to open the text brackets now. I'm just going to put whatever numbers. So up to 9K is 10%. So it goes like this. And then it's 15%. Let's say from 9K to, I don't know, 35K, whatever. And then it's, that's the 25%. So that's a 10% jump because the most people are in that bracket. So closed circle here that was open below. It goes, I don't know what the numbers are, but I just needed one jump. So you're looking at this graph and you're asking if it's continuous. Now you see it's not continuous, right? Clearly not continuous. But let's run the rules. How about continuous at 9K, 9,000? Is it? Clear answer is no, because we have eyes. But let's show the work, right? So number one, let's call this t of x, right? Does t of x exist? T of 9K, so taxes for 9K. Do you pay taxes if you, right? Yes. So does the value exist? Of course. What is it?
15%.
It's 15%, yes. 15%. So you will pay taxes for 9K exactly. And it's 15%. Good. Or not good. How about 2? Limit for the tax function as x approaches 9K. 9K is me not writing 9,000. Anyone? So half of the class, well, half of those that are shaking their head, it's either no or yes, and you said yes. So are we taking it outside, or we're gonna figure it out here? Yes, from left and right. Romeo and Juliet, they don't end up at the same spot. Look, from the left, you're going to 10 on the y-axis, and Romeo from the right is going to end up at 15, right? They're not at the same location. So limit, DNE, does not exist. So Theorem 2.2 states, if the left and right limits are the same, overall limit is that value. Limit from the left is 10, limit from the right is 15. So at 9K, two separate values, no limit. So is it continuous? No. We see that, and we just used math to show. So we have notion of continuity at the point where the graphs that are piecewise either plug nicely, like in the previous case, or they don't, like in this case. Now I'm going to draw 3 different graphs. And first you will tell me what's common for all 3 graphs, and then we'll figure out what can we do. So what is common for all three graphs here. Yes. What does that mean? Yes. So all three graphs are discontinuous. All three of them. Discontinuous. You want to write that in your notes? Go ahead. All three graphs are discontinuous. Now, that means that one of the three rules had to be broken. So I have rules 1, 2, and 3 for each one of these. And since all of them are discontinuous, at least one of the rules, maybe two or all three, had to be broken in order for it to be discontinuous. If they all three pass, then it's continuous. So the first rule is what? Function value does not exist. Yes. It fails on the first rule. You see that there is no f of a. If this value here is a, f of a does not exist. There's no value there. There's no y value for it. Cool. How about the second graph? Do we have f of a? Yes, f of a is right here. It's where the filled-in dot is. So we do have f of a. It passes. Do we have a limit? No. Always stick. Left, right, right. Romeo, Juliet, they don't meet at the same point, therefore fails right there. As soon as it fails one of these, it's gone. All right? You don't mess around with it. How about the third one? Does the function value f of a exist? Sure. It's right here, called f of a. Pass. Does the limit exist?
Yes.
Yes. Nice. It's right here, L. Are they the same value? No. All right. So this is how you construct three examples to show what exactly means for one of the or particular rule to fail, right? So we have function value does not exist on this one, and done. The function value exists, but the limit does not exist. That's dead. And then over here, function value is there, limit is there, they're not the same, therefore, again, not continuous. So you can visually see that all of these are discontinuous graphs, and then discontinuous bridge. Part of the bridge is missing. You don't drive over that, right? Good. Next. Global continuity. So function is continuous globally if it's continuous at every point in its domain. Function f of x is continuous globally if it is continuous at each point in its domain. How many points do we have in the domain? Infinite. Does that mean that if I want to test the continuity of x squared, I have to be an elf? Right? Live forever and just keep plugging all of the points?
That's where you go if you've been that person in life.
Wow. What, Middle Earth?
Yeah.
You go to Middle Earth. Nice.
The thing on the planet.
So, yes. So, there are certain proofs that you do later in mathematics. Right now, we stuff all of this into one theorem. And that theorem says following functions are continuous on entire domain. And you memorize that. So that later, when you have to figure out continuity, you call upon that theorem and you just say, we know. Because there is a proof somewhere out there in mathematics world that says that all polynomial functions are continuous on the entire domain. Sine, cosine, e to the x, right? All of them are 1 over x? Not so much, right? So, theorem. Following functions are globally continuous Now, I'm not going to say on the entire domain because that's what the word globally means. Means at every point in its domain. So I'm not going to write that. Polynomial functions, meaning p of x is equal to a0 plus a1x plus a2x squared plus a3x cubed plus going on forever. You can have polynomial of any order. Guys, this includes polynomial y equals 7. That's just a horizontal line. That's just at a0. So line y equals 7 is continuous forever. Sine x and cosine x, obviously. E to the x, ln x. We know that the domain of ln x is from 0 to infinity. But that's all there is for it. So that's why it's continuous on its entire domain. The word globally patches that. Right? You don't say it's discontinuous because it doesn't have anything left of 0. No. Its realm of existence. Its realm of existence is 0 to infinity, and it doesn't have interruptions for its lifespan, say it. Square root of x, right? So rational, radical functions. So all of these functions, sine, cosine, e to the x, ln x. So which ones are tricky? Not continuous. Obviously 1 over x. All the rational functions, which could have vertical asymptote, which is the break in the domain. No coffee. Tangent x, cotangent x, secant, cosecant. What else is there? I mean, a lot. A lot. I kind of want to add to this list inverse tangent of x. I'm going to draw the function. Looks like this. That's continuous. Has 2 horizontal asymptotes, negative pi over 2, positive pi over 2, but on the domain from negative infinity to positive infinity, perfectly continuous. Okay, now, a little bit of terminology and the fact that you have to be very careful with the words you use with continuity. Y equal 1 over x. Now, from 0 to infinity, continuous piece. From negative infinity to 0, also continuous piece. Globally, so from negative infinity to positive infinity, not continuous. So this is what we mean piecewise continuous. Pieces, individual pieces are continuous. So if I have a theorem later on that has continuity as a prerequisite, if the function is continuous and differentiable on the interval, blah, 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 this happens, blah, 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 this happens, and so on. That means that that theorem doesn't work on this particular function because function is not continuous. However, that theorem will work on half of this function because that piece is continuous. So you can't look at the function as a whole and apply that theorem later on, mean value theorem, let's say. But you can look at the piece, you can restrict the domain and say, I'm only going to look between 0 and infinity. And in that case, it becomes continuous, and you can use that theorem later on. So you have to be very careful with wording and difference between continuity at the point, continuity of the pieces, and the global continuity. So they're all different, but they're obviously intertwined. Cool. That's it. The final piece is to see the properties of continuous functions in a sense that when you add continuous function to another continuous function, the sum is continuous. Same happens with subtraction, multiplication, division if you don't get 0, squaring or exponents. So all of those properties are there. Yes? Why, sorry for stretching. Yeah, I know. So Theorem 215 establishes continuity of functions. Oh, they didn't. So, okay, so this is bad. All right, this is one of the reasons why I'm not too keen with the book, because look, they put a tangent there, and they didn't say. They said their domains. Domain of tangent is negative infinity to positive infinity, and it's not continuous because it has a vertical asymptote every pi over 2. So these guys are continuous on the what we call a restricted domain. It's piecewise continuous between negative pi over 2 and pi over 2. This one is continuous from 0 to pi. But they're not continuous overall, so they shouldn't be on this list. This is perfectly fine, obviously, and it's perfectly fine because these come from the restricted domains. They were actually not inverse functions until we fixed the domain. Once we fixed the domain, we also addressed the issue of continuity at the same time. So everything on this list is cool except these 4. They have to be kicked off. Unless you put in their restricted domains just for these 4, and the other ones were fine to begin with. So I don't know. That has to be fixed.
That's why they can print more books.
What happened?
I said fixing that out was like $1,000. That's why they can print more books.
Yes. Which is why I write this and upload and then.
Which was the 4 you said? You said tan, cotangent?
And secant and cosecant underneath. Oh yeah, for you guys, that's going to be actually very important. It's a little detail that, yeah. All right. Cool. So we did that. Here is the story of trigonometric functions. What you see here is secant x graph on the right, the one with lots of lines. So that's a secant x, and you clearly see it's discontinuous, right? But each one of these parabola-looking pieces, each one is actually continuous. So this one is piecewise continuous, not globally continuous. So technically, if someone says if it's continuous, they're immediately implying for the global continuity, and you say no, right? And if you try to do, something fails. Limit, function value, whatever. Roots, transcendental forms. There is one more thing before intermediate value theorem. Where is the thing that puts all the functions together. Addition, subtraction. Oh, yeah, this book puts that over 6 pages. Yeah. Anyway, I'll give you that theorem free of charge. Combinations. Oh, thank you. Combinations of continuous functions. So, if f of x and g of x are continuous, then f of x plus g of x, f of x minus g of x, f of x times g of x, f of x divided by g of x, where g of x can be 0, f of x raised to the power n, f of x raised to the power n over m, and f of g of x, function composition, are all continuous. And you guys are going to use this in Calc 2 when you do chapter on sequences and series. I might be able to find exactly, but you are technically writing a paragraph. So let me try and find the problem from the last semester so you can see exactly how it goes. Where's my integral test? Right here. All right, so we are looking at a calculus 2 now. And I'm looking for, so in order to do this thing in calculus 2, you see that the first thing that is checked off there says continuous, right? So you actually have to know the concept from Calc 1 to do. Then the next one is decreasing and then the positive. So that's conditions so that we can do what we're doing. And, so this is an example of it. So you have this crazy thing that you have to transform, and the condition is that you need continuity. And here is the proof that you do in the Calc 2 class. It's not honors class, it's just a regular Calc 2 class. You have to do this to establish continuity so that you can actually do the problem using integral test. And look what it says. X is a polynomial, therefore it's continuous. So that's x is a polynomial, that's that one. ln x is continuous, that's all from the theorem we just stated. Combinations of continuous functions are continuous. That's this last thing, last blurb where I said if you add them, if you multiply them, if you square them, and that's the combinations. Look, we're dividing them, we're squaring them, multiplying them. Combinations of them are continuous. And x cannot be 0 because we are starting at x equals 2, okay, and then x equals 2. So it can't be 0, and ln can't be 0 either. So, boom. The whole thing is continuous on the domain. And the domain is 2 to infinity. So you are not learning this theorem now to pass Calc 1 test unless you're done with math career. Here it is, use it, all we learned today, everything. In just the first step of the Calc 2 problem. And then you have another 2 proofs, right, for positive and decreasing. And then you get to do the Calc 2 problem. So learn this stuff. Don't do that. Sneeze. The back pressure can detach your lung. Yep. We'll deal with whatever happens after that. With the aftermath. Let's use the word in the calculus. We'll deal with the aftermath. All right. Oh no, wait. I have to switch to Calc 1 now. All right, going back to Calc 1. So you've seen all of the rules that we just learned in these last few theorems used there. I used the polynomial thing, use this one, use ln, and then use this to show and establish continuity. Okay. We have one more. Well, let me see if we can find more problems. Yeah. Just a little bit, sure. A little bit more? All right. Or you want to see the whole theorem? The whole theorem? Okay. That is different because I'm, I was trying to do exactly what you wanted. It's a math class. It's important for you to be happy. So I'm going to switch to the textbook. May I? And I'm going to bring up these problems 9 and 10. These are good exam problems, for instance. What fails in terms of continuity? Clearly not continuous. Which rule fails at 1, which rule fails at 2, which rule fails at 3? Right? Technically, I had those 3 separate graphs. There they are all mushed in one exercise. You have the same thing for problem 10. Right? So now you have to figure out which rule fails over here. Number 1, number 2, number 3. Number 3. You do have functional value. You do have limit. Task 1, task 2. They're not the same. Fail number 3. That corresponds to this one over here as well. Right? So you must learn theorems and definitions in order to answer any of these questions. It's no longer monkey sees, monkey do. We left that behind in algebra. Yes?
So if you got x of 1 and then you got x approaches 1, how do you have 2 different values?
Well, it's open circle, right, which means value is not there. And if it's a filled-in circle, value is there. So in that case, the limit is at 3, and the functional value is at 2. So f of 2 is 2, limit of f of x is 3.
How does this happen?
Because when you approach from the left, you approach from the right, the answer is 3, right? That's the limit. And when you plug in the values, f of 2 is where the value is.
So that's if you didn't factor it out?
No, that's just
If you don't factor, you get...
we don't even have, look, we don't have fraction. We don't even know what the function is. We have no x's, x squared, or anything like that. We don't know. We just have this. So this one over here, this point, is a limit f of x as x goes to a, and this point here is a f of a.
But it's the same function,
Yes, it is.
and you could use the same number.
It is. X equals a.
Yeah.
The value of the limit and the value of the function are not necessarily the same. They have to be the same in pre-calculus, which is what the limitation of pre-calculus is. In calculus, they don't have to be the same. That's the best explanation for that would be, this is what you were supposed to do, but you were doing something else. What's the speed limit on 78? And what are you driving?
At least 70.
Okay. There we go. So that's that. All right. This is what you were supposed to do, and this is what you're doing. Does it make sense? All right. Good. Welcome to reality. Welcome to reality. That's all I can say.
What's reality like before the 1600s?
You bang two rocks to make fire. Put all of your garbage through the window on the street. Right?
Will somebody else take their land?
Yes. It
Yeah,
was.
right. When,
Yeah.
Disputes could be settled through duels.
Exactly. Right? And then we discovered calculus.
And the duel, yeah.
Everything changed. We duel on a different level with bigger weapons. Yeah. And you have internet trolls. That's what it is. We benefit greatly. Awesome. One more thing. The intermediate value theorem, which from computational stand we don't use anymore and we don't need it. It was essential 400 years ago or even 200 years ago. Damn, even 100 years ago. But now we have calculators, computers, software, stuff, so we don't have to do this. The value of intermediate value theorem is in should I put this? This is what solving equations actually means. Let's put it that way. So when you want to solve equation x plus 3 equals 5, you know that you are supposed to subtract 3 on both sides, get x equals 2, and be done. But technically, the true form of this equation is x plus 3 equals 5 is minus 5 on both sides to get x minus 2 equals 0. And then you graph this thing, this equation, and you see that it crosses the x-axis at 2, which is this. All right, so what the hell happened there? Intermediate value theorem states that if the function is continuous, you have two values on the x-axis, a and b. It will have f of a and f of b, obviously. If you pick a value f of c in between a and b, if you pick value c in between a and b, there will be f of c in between f of a and f of b. Intermediate value theorem. On a picture. Here we have a continuous function f of x. I have a and I have b. A will have a corresponding f of a answer on the y-axis, and the b will have a corresponding f of b on the axis. If I pick any c anywhere in between a and b, say right here, its f of c will be between f of a and f of b. And that only works if function is continuous. If the function is not continuous, I would be able to find f of c outside of the interval. Now, why is this important? As I said, we don't use it anymore for any kind of calculations, but it's important for the purposes of solving equations to understand what that means. Because we know that if you have f of x equal to 0, that's the root, also known as a solution or x-intercept, right? Or 0, all of these words that you learn in pre-calculus. And if you have that right here, So there's that x value c. You can see that all values before, in this case, were negative, and all values after that were positive in y. So you can technically solve any problem this way by guessing the interval and then just zooming in. So it's a really tedious work, but it works. Let's say you are trying to solve x squared equals to 3. This is really nothing of an example, but yeah, there it is. So x squared equals 3. You know that x squared minus 3 equals 0 is something that you can graph. So x squared, let's graph underneath. X squared minus 3 means it's going to dip below to negative 3 right there. You are looking for this number. You know the other one's going to be symmetric. So you want to know what number is this right here. So you make initial guess. That the value that you are looking for is between 1 and 2.